we go. Now, any issues that we need to deal with now before we get into the next chapter? All right, so I'm going to share the PowerPoints, start the show, slideshow, come on. There we go. Okay. Move some of this stuff out of my way so I can see what's going on. All right. So when we started in Gen Chem 1, it was pretty much, there was a lot of memory going on at the beginning. You had to memorize the elements of the periodic table, and we came on and introduced some laws, and you had to memorize those. And only sporadically was the concept of the why, the theory, introduced. Now, it did come along, of course. We try to give you as much of theory as possible. But Chapter 17 is very heavily weighted toward theory. It's trying to explain why reactions occur spontaneously. And now, of course, I've got to define what that means. So let's start with the comparison of kinetics, which we've studied already, and thermodynamics. The kinetics addresses how fast a reaction occurs. That's all it does. Thermodynamics looks at whether the reaction will even proceed spontaneously. And spontaneous means something will happen without any external intervention. Right, so once the reaction, and once the proper conditions are there, then the reaction will proceed without any action from the outside. So this diagram we use to illustrate what part of the reaction each addresses. The kinetics addresses this middle part, where we see a rise in energy till we reach the activated complex, right? We have to put in so much energy to get there, and then heads down the other side. So we know that the reaction will proceed faster if this hump is smaller. And the reaction itself does depend on whether it, on the path it takes, right? And we approach that subject in kinetics, particularly in terms of the use of catalysts. Catalysts provide a different pathway, a pathway that requires less energy to go from reactants to products. So the pathway is important in kinetics. It's essential. Whereas thermodynamics is only concerned with what state are the reactants in, what state will the products be in, and compare those two, and then you draw some conclusions about whether the reaction will proceed without any external intervention, in other words, spontaneously. Okay. So, with those facts in mind, we say that the kinetics description of a reaction in terms of kinetics is a path function. In other words, the path matters. what path does the reaction take? Whereas thermodynamics is only concerned with the state of the reactants in the beginning and the state of the products at the end. So it is a state function. It doesn't matter what the path is. Okay. So as we said before, the study of thermodynamics allows us to predict whether the reaction is spontaneous in the forward direction, whether it's spontaneous that way, or whether it would be spontaneous this way. Because if it's spontaneous one direction, it's non-spontaneous the other. It can't be both. And of course, you'll notice those double arrows as an equilibrium situation. All right. So let's take this example. We're trying to explain why a reaction occurs. And we've alluded to that over the many chapters in this class and in Gen Chem 1. What are some driving forces for reactants? And we discussed things like if a gas is produced, if heat is evolved or temperature is involved in some way. You can tell a reaction is occurring if you see light evolved, or if you sense a temperature change, either a decrease in temperature or an increase in temperature, right? Because some reactions are exothermic and some are endothermic. But those were more or less rules of thumb. Now we want to try to explain why certain reactions occur even when we can't detect the obvious reasons for that reaction happening. And here's an example. Now, recall that chemistry is often referred to as the central science, which is another way of saying that sky's the limit. If you study chemistry, you can go anywhere. In fact, you can encroach on physics. You can encroach, you can delve into biology. So with that respect, we're going to look at this system in this concept and recognize that there really is no chemistry going on here. But the process itself is spontaneous, and we want to try to explain that. This is a physical system. There's no chemistry here, but we can describe the process itself as either spontaneous or non-spontaneous. So let's look at the circumstances. Say you have 2.4 moles of gas in a 4-liter bulb. So you have a 4-liter bulb here, and you have 2.4 moles of gas. Okay? That bulb, is at 32 degrees centigrade. And it's connected to another bulb, a much larger bulb, which is 20 liters. Right? So they're connected here. And there's a valve right there. And at the beginning, the valve is closed. So over here, you have a vacuum. Right? And at the same temperature. Right? So that's the situation before we do anything. The one constant in all of this process is the temperature. We're not going to let the temperature change. Right? Because if we let the temperature change, then that draws our attention toward transfer of heat. And that might make us explain what's going to happen in terms of the transfer of energy. But this is going to happen even at constant temperature. So if we open the bulb, what's going to happen? Well, obviously, when you open the valve, all right, I don't have a cue there. When you open the valve, this gas is going to rush into that vacuum to fill that space. But not all of it. Right? Some of it's going to stay behind. And as long as the valve is open, the pressure in those cylinders is going to be the same. But the question is, in a chemist's mind, why didn't all this gas stay right there in that bulb? And that sounds like a stupid question. But this is a thought experiment. We know that what's going to happen is the gas is going to move that direction. But we can't define any driving force other than the fact that there's a difference in pressure. So how do we explain the fact that the gas moved into that space? And this brings us to the a new concept that's required to explain what's happening. But before we do that, I want to go to the next slide and refresh your memory on some terms. Okay? Remember back in when we studied thermochemistry in first semester, general chemistry, we defined these terms. Let's start with delta E first. The total internal energy of a system. And remember how we defined a system. A system has a boundary. Right? And everything else is surroundings. Okay? And we can define things that we can describe our system and its relationship to surroundings with these terms. Right? So delta E is the total internal energy of the system. And that includes all the kinetic energy, all the potential energy that's contained in that system. We can define things that happen across that boundary in terms of either heat flow, right, Q, or change in work. Right? So if the heat flows in, everything's relative to the system. If heat flows in, that's a positive value. If heat flows out, it's negative. If heat flows out, it's exothermic. If heat flows in, it's endothermic. If the system, if we do work on the system is gaining, so that's positive. If the system does work on the surroundings, then it loses some internal energy to do that, and that's why the value is negative. Okay? So we define Q and W, delta E, in terms of internal energy. Then there's this term enthalpy, which is not necessarily equal to Q, right? It is a thermal property, right? But Q and delta H are only equal if the if this term pressure volume does not change. Okay, so now that we've got those terms refreshed, the next question is, in the system that we described earlier, what's happening to these terms? The delta H, delta E, Q, and W for the process. Right? The shorter answer is all the values are equal to 0. there's no change. There's no change in enthalpy, there's no change in internal energy, there's no transfer of heat, and there's no work being done. So let's look at each one. How do we know that enthalpy and energy are zero? We know that because the temperature did not change. And we also know that because the pressure, the gas is working against zero pressure. So that term is zero because there's no pressure. So the work function is zero. If the gas is expanding against, and there's no force being applied, remember, work equals force times distance. If there's no force being applied against some resistance as the gas expands into the vacuum, then there's no work being done. Right? So that's why W is zero. And then the relationship of delta E to Q and W says that since delta E is equal to Q plus W, our internal energy is equal to heat transfer and work transfer. Then work is zero, and Q has to be zero also because there's no change in temperature, right? You can't have a change in heat if there's no change in temperature. There's no flow, no heat flowing in or out if the temperature is constant. Right? So all of these values are zero. So that begs the question, if we know all of these values are zero, why did it happen? Right? There's no change in any of these values, so we can't explain what happened in terms of those values. Right? We need a new value, as luck would have it. And the driving force for that process then is called entropy. Here we go. Entropy. And we give it the symbol capital S. All right. What do we mean by entropy? Well, entropy is kind of a difficult concept to grasp. So we're going to start off with simple concepts. Even if they're not entirely accurate, they'll give us a foot in the door to understanding entropy. So here we have our example of the gas expanding into a vacuum. And notice what the difference is between the images. Right? You've got the same moles of gas here as you do here, but notice here they're spread out farther apart. Okay? So we could identify that as disorder. Right? We've increased the number of places that those molecules can occupy by giving them more room. So we've increased their disorder. And that's one way of thinking of entropy. An increase in entropy is an increase in disorder. A decrease in entropy would force those molecules into a smaller space or into a more regular arrangement. We'll look at some examples in a second. So we have the molecules in a larger space. That, in a nutshell, is the driving force. Because nature, I've often heard it said, nature abhors a vacuum. If there's any way that matter can get into a vacuum, it'll find a way. And the reason is it wants that space. So we've increased the entropy, and as a consequence, If entropy increases, the value is going to be positive. If it decreases, the value is going to be negative. Now, we've defined our term S as entropy, but entropy cannot be measured directly, right? So we cannot measure that value S. We can only measure a change in S. And in fact, we can't even measure a change in S. We can measure everything else, and S is a calculated value. Okay, and I'll show you how to do that later. But in fact, we're looking at delta S. Sometimes you'll see formulas where the deltas are left out of the formula. That's not strictly speaking correct, because we don't measure absolute values. In fact, I can't think of a single one right off the top of my head. We always measure a difference. We have to reference to something. So entropy is delta S. Actually, a change in entropy is what we're measuring. So if we look at this driving force for a spontaneous process as entropy, and the increase in entropy is required for the spontaneous process to proceed, we say that if we increase the order, delta S greater than 0, then we expect that the randomness or disorder is increasing. And that is one driving force for the reaction. Now, if we hold everything else constant, then entropy is the only explanation for a spontaneous reaction. But if we let some other things vary, then they also enter into the explanation of a spontaneous process. Right now, we're focusing on entropy. And this is just a caveat. Disorder, the term disorder is really oversimplified explanation of entropy. But like I said before, it's useful as an introduction. In reality, entropy is a thermodynamic term that is actually has a statistical foundation. In other words, what is the probability of one state versus another state? If the probability is higher for this state, then that's where you're going to find the reaction going. And it turns out the probability of having lots of molecules in a larger volume, that probability is higher than having all those molecules in a smaller volume. So then you get the driving force in terms of probability to create that spontaneous movement from small volume to large volume. We often term that, we often say that this function describes the number of arrangements. So if you increase the number of possible states for your system, then that's the direction it's going to move. Have I confused anybody? Well, you might be you might be reserving judgment until we actually start processing the information in real examples. That will help, I guarantee it. So, what do we call these numbers of states? Well, we call them microstates. So, in this case, we've simplified our situation where we only have, okay? we simplify our system to where we only have 4 molecules. And if we have these 2 bulbs, what are the number of microstates that you can have where all of the molecules are in one side? There's only one possibility. All of them are on one side. There's just one possible microstate for that one. Or on the other side, there's only one possible microstate for that one. How many possible microstates are there if you move one molecule at a time into the other bulb? Well, if you move A over here, that's one possibility. If you move B over here, but not A, or C over here and not A or B, and D over here and not A, B, and C. So you have 4 possibilities there. We've increased the number of microstates with this scenario. So based on our previous argument, it's more probable that this arrangement, number 2, Roman numeral 2, is more probable than this one. But what if we move 2 over there? Well, if you move 2 over there, then you have 6 possible arrangements. And this one is more probable than either of these 2. Now, if you do the converse, if you say move 3 over here and leave 1 behind, that's what you get down here in arrangement 4. And again, you only have 4 states down there. So the most probable arrangement is the one with the largest number of microstates. And these 6 microstates say that this arrangement is the most probable, and as it turns out, half the molecules are over here and half of them are over there. That is, assuming these bulbs are both the same volume. Then that argument works. Okay, so the microstate concept is arriving at a true explanation for what entropy is. The number of microstates possible. Oops, couldn't see that. Okay, so there's your definition of microstate. We just went through that whole process without defining it. So I sort of got it backwards. Now let's look at some examples. We're still talking physical change. Right? So, what are the possible number of microstates for a solid? Well, they're not that many, especially for a crystalline solid. A crystalline solid pretty much locks all the components. They might be ionic. They don't have to be, but they might be ionic. They could be covalently bound, like in a diamond. But it's a crystal state that locks all the molecules into a regular pattern, and it's highly unlikely that they will move into a different position, which would give you another microstate. So in the perfect crystal, you would expect that there's only one microstate for this particular crystal. Now, if you form the crystal again, you might get a different, but you still would be limited to the number of possible microstates for a solid. Whereas in a liquid, there's enough energy there for the molecules to move past one another. So you have many more possible microstates in the liquid. If you form the gas, you've exponentially increased the number of possible microstates in a given period of time. Over time, you have so many microstates here. In a gas, there's so much energy there that at any given micro nanosecond, you could have any number of microstates. So what we're saying is that the entropy, and here we've left out the delta, the overall entropy of the solid is less than the entropy of the liquid, which is less than the entropy of the gas. Okay? So if we revert to our earlier concept of disorder, I think it's fairly easy to see that the solid is more orderly, the liquid is less orderly, and the gas is even less orderly still. So let's see if we can predict the sign of delta S for each of the following. Remember, increasing entropy is a positive sign. So how about the evaporation of alcohol? You're going from a liquid to a gas, right? So we should see there it is. We should see a positive entropy. How about freezing of water? It's going from a liquid to a solid, right? So we should see a decrease in entropy. What if we compress an ideal gas at constant temperature? You're forcing the same number of molecules in that gas into a smaller space. So you're decreasing the number of possible microstates that they can occupy. So you should expect that also be a negative change in entropy. What if we heat an ideal gas at constant pressure? What happens when you heat a gas at constant pressure? Let's see. Didn't say anything about the volume. So if the pressure is constant, that means you heat it, the volume has to increase. So that would be an increase in entropy, correct? What if you dissolve sodium chloride, table salt, in water? In the beginning, you only have one molecule each. When you dissolve sodium chloride, you end up with two particles. So that reasoning alone increases entropy. But on top of that, you have a regular crystal structure of sodium chloride being broken apart into a whole host of different possible microstates in solution. So that would give us an increase in entropy as well. I hope it's starting to make a little more sense. Okay. So that brings us to the laws of thermodynamics. I think I may have mentioned this. I'm pretty sure I did. In I think it was chapter 6 that we reviewed from the same textbook in Gen Chem 1. I may have alluded to the first law of thermodynamics. Right? It just says the change in energy for the universe is zero. In other words, you can't create energy, you can't destroy energy. That's the conservation of energy law. That's the first law of thermodynamics. The second law of thermodynamics incorporates this concept of entropy. So, for a spontaneous process, there's always an increase in entropy. Now, when we say increase in entropy of the universe, the way the authors use universe, they sort of interchange universe with rather than universe, total. So let me explain what I mean by that. We have a system, we have surroundings, right? Okay, so we've defined those. But if you isolate these two together, you have a total. Or you could call this our little universe. Rather than the whole universe. See what I mean? So what I've tried to do in these slides and in your review documents and even on the exam, is to be very specific. If I give you a problem, I generally define it in terms of total for an isolated system and surroundings. Okay? Now, this isolated situation can either be for the system and surroundings, or it can be for an isolated system. Remember, before the lockdown, we had done a chemistry experiment where we had an isolated system with our two styrofoam cups, and we had a reaction going on inside the system, and that system was isolated so that we could say everything that happens in Vegas stays in Vegas. Right? But we can talk of system and surroundings as also isolated, and in that respect, we define that as total, not universe. But when you're reading the textbook, the authors often conflate universe and total. Okay? That's just a warning. So the second law of thermodynamics says that the entropy of the universe, and this is true for the entire universe, not just total, the entropy of the universe is increasing. So for the universe, that's the true universe. Everything is always positive. You may have heard the expression, the universe is running downhill. Right? That's what they mean. It's all the whole universe is heading toward absolute zero. That is, eventually, well, there's some argument among physicists whether the universe is going to end in just a cold nothingness, or whether it gets to a certain point and then it rebounds on itself to a big crunch. But at this point, this law holds. The change in entropy for the universe is always positive. Now, we've already determined that the change of entropy for a system can be either positive or negative. And for an isolated total universe and system and surroundings, the value can also be positive or negative. So that's why I decided to say this is the preferred way of describing the entropy, the total entropy of our system and surroundings is the summation of the change for the system and the change for the surroundings. So what that means is, if the entropy of the system increases, the entropy of the surroundings must decrease. Okay? Because if all of this is isolated, then the total can't change. All right. So let me see. I'm going to get that out of the way. There we go. That's not what I expected. Move that. You guys can't see what I'm doing, but I'm trying to, I've got things in the way, and I'm trying to make them visible. Okay. So, the change in entropy for the universe in our, I forgot to change that one. The change in entropy total predicts spontaneity. So if you can say that the change in entropy is positive, then you would expect the process to be spontaneous. Whereas if the change in entropy is negative, the process is spontaneous in the opposite direction, right? Or non-spontaneous in the forward direction. And also, here's a good one. If the change in entropy is 0, then we are at equilibrium. That's a good one to remember, especially when we start solving some of our problems. If the total entropy change is 0, then the process is at equilibrium. All right. So here's a concept check. Here we have whatever this is in the liquid form in equilibrium with the solid form. So which direction involves an increase in energy randomness? Okay, we're introducing two new concepts. Before, we were concerned primarily with positional randomness. That is, how many places can your molecules be at any one time? Right? What positions can they occupy? That's positional randomness. But we can also apply that to energy randomness. So let's see if I can explain that. If the process is exothermic, that is, we're going from liquid to solid, right? For our system, if our system is going from liquid to solid, then it has to give up energy to its surroundings, correct? So if energy is leaving the system, we would say that the energy randomness decreases from going from liquid to solid. Right, we're losing energy, so the energy randomness is on the decrease. We have less energy in our system. So energy randomness favors the solid formation, the forward direction. What about positional randomness? Positional randomness favors the formation of the liquid in the opposite direction. So in the forward direction, our positional randomness is decreasing, going from liquid to solid. But our energy randomness is, our energy randomness is also decreasing, going from left to right. And our positional randomness is decreasing, going from left to right. So they're both increasing, going right to left. Right, and decreasing, going left to right. So what does that mean for, well, that was just a concept. Actually, we introduced a new concept there, didn't we? It wasn't just a concept check. Energy versus positional randomness. And I suspect that what we're interested in is, in any process, you may have both acting at the same time. Now, if they're both, randomness is increasing for energy and for position, you would expect that the process would be favored in that direction. In this case, it would be in the reverse direction, would be favored. But it's possible to have energy randomness going one direction and positional randomness going the other direction. And in that case, you have to see which one wins. And the summation, the vector summation of both of them, will tell you which one is positive. The summation would be positive for if one of them wins out. So let's see if this example helps any. The question is the temperature increasing or decreasing? Which takes place? Energy randomness or positional randomness? Well, as the temperature increases, positional randomness obviously dominates because you're producing many more microstates as you increase the energy of the substance. So as temperature increases, positional randomness is dominant. So, what's the situation at high temperature? Well, at high temperature, the positional randomness still dominates because the release of energy, the very small release, an incremental release of energy at high temperature has very little effect on the randomness of the substance. Whereas at low temperature, a change in temperature, okay. All right, let me back up. We've got a competition. Let's put it this way. Let's see if I can explain it a little bit better than that. So we've got a competition between energy, let's say S for energy and S for position. So there's our entropy for energy and entropy for position. They're in competition. Which one wins? Well, it depends on the temperature. As the temperature increases, the positional randomness becomes more important. So this one dominates. And then we look at the positional randomness at different temperatures to justify that conclusion. Okay, so at high temperature, you have a huge number of microstates that are available. That's why positional randomness dominates at high temperature. As the temperature increases, it becomes more dominant. Why? Because the little change of temperature has very little effect on the amount of energy that the system contains. So the energy randomness is less important. Whereas if we decrease the temperature, then the energy randomness dominates. Because the change in entropy at low temperature is much more significant with an incremental change in temperature, like 1 degree centigrade, at very low temperature, has a marked influence on the entropy of the system, much more so than it does at high temperature. I don't know if I explained that very well. Example. As you decrease the temperature, what happens to your substance? Well, it goes through gas, liquid, solid. So overall entropy is decreasing. But what's the effect of a change in temperature on the entropy at very low temperature? Well, say you've got the temperature low enough to have a solid. If you write it, if you're at the melting point, then a little bit of increase in temperature will have a huge impact on the entropy. It'll go from solid to liquid. Or if you're at liquid-gas interface, then a change in temperature will go from liquid to gas, and then you have a monstrous increase in entropy. So the lower temperature is dominated by a change in energy, an entropy change in energy. Whereas at high temperature, the molecules are already random. They're hugely random. So a change in temperature has very little effect on their randomness, and then the position is the primary focus for judging entropy of the system. Does that make any better sense? I hope it does.
Dr. Bly?
Yes.
I have to go for my appointment.
Oh, okay, sure. Yeah, I'll post the recording. No problem.
Thank you. All right.
Okay, so then the question becomes, at what temperature is there a balance between randomness and positional? Positional and energy, excuse me. Positional and energy randomness. Well, the short answer is at some point of equilibrium. And that occurs at either melting point or boiling point. Because when you've reached that point, you can have both phases at the same time. So then you've got a change in positional entropy from one phase to the next, and a balance of energy randomness as you input a little more energy to go from solid to liquid or from liquid to gas. So at the melting point, we find that the energy and positional randomness are in balance. All right. Let's see if we can make sense of, can we say spontaneous, non-spontaneous, or there's not enough information? So let's look at these examples. So if a reaction is exothermic, right, it gives off energy, but it becomes more positionally random. So let's see if we can conceptualize that. So we've got our system and surroundings. And if the reaction is exothermic, what happens? If it's exothermic, then Q is negative. Right? We're losing energy from the system as the reaction proceeds. And also, we're saying that the system becomes more positionally random. So that is delta S for position is positive. So can we say, is this spontaneous or non-spontaneous? Well, what's happening to this one? Energy randomness. It's losing energy, right? So this one should be decreased. So energy randomness for this system is decreasing as the positional randomness is increasing. So what conclusion can we draw from that? Well, now based on what I just drew, that doesn't justify the answer. Both driving forces are favorable. In order for both to be favorable, you've got to increase both. That one definitely is positive. But I would think that if it's exothermic, we're losing energy. So I haven't explained that one very well. Both driving forces are favorable. Hold on just a second. Let me see how the authors approach that. Well, they don't. I would tend to say that this is you can't tell because you don't know. I'm going to have to look into that one a little closer. I never noticed that before. But based on our previous definitions, that definitely positional entropy is increasing, as it says it is. But if it's exothermic, then the system is losing energy unless they're talking about total. If they're talking about total, then yeah, you're moving energy into a larger space. So energy randomness then would also increase. That's the only explanation I can give for it. So I'll dig into that a little deeper and see if that explanation is valid. Let's see if the next one makes any sense. If it's exothermic and becomes less positionally random, in that case, based on their definition, I would say you can't tell. Exothermic is favorable. That's the only thing that's possible. If you say delta S energy for total, yes. And energy total, that's energy total. Randomness is also. But in order to say that the randomness decreases for the system, then you would have to say which one dominates, and it depends on the temperature. And we don't know that. So we cannot tell for this one. That's true. I can see the logic. If we say this one is spontaneous because exothermicity gives the energy more places to occupy. So if it's endothermic and more positionally random, then you can't tell that one either. For the same reason as B. Because it depends on the temperature, which one dominates. If it's endothermic and less positionally random, then it's not spontaneous. Okay, so to recap, if you have an exothermic reaction that's more positionally random, you have a spontaneous. If it's endothermic and less positionally random, you have a non-spontaneous. And then the other possibilities depend on the circumstances and in particular the temperature. So we can't always say that exothermic is spontaneous or that endothermic is not spontaneous. Depends on the circumstances. Endothermic, exothermic doesn't tell the whole story. I see that as the moral of this slide. All right. So let's look at some possible calculations. We have to look at calculations because entropy cannot be measured directly. Not like enthalpy, right? We can determine heat by a change in temperature and the amount of substance and other factors that may be involved that we explored in our in Chapter 6 in thermochemistry. So the entropy of the surroundings can either go up or down. And it can depend on the direction of the heat flow, right? Does the heat flow out of the system into the surroundings or into the system? So that would imply, if it's exothermic, if heat is flowing out of the system into the surroundings, we would expect the energy randomness to increase as you're providing energy more space to occupy. So as heat leaves the system, randomness in the surrounding increases. And actually, it also provides, as you provide more energy to whatever is in the surroundings, adding that energy, I think, has an impact on the positional randomness of the molecules, because you're adding energy to those molecules and they're moving faster. So at any one point, you could have a whole host, a greater number of microstates available. So as the heat leaves the system, the randomness in the surroundings increases, right? So for exothermic, you would expect that. And as heat enters the system, you would expect the randomness of the surroundings to decrease. And the magnitude of that depends on the temperature. Why? Because a change in enthalpy also depends on temperature. Now, this change in entropy is it's felt greater by the surroundings if you start from a position of lower entropy than if you start from a greater entropy, which in general refers to the temperature, right? So at higher temperature, you have lots of entropy. So the change in entropy on a percentage basis is much less. Whereas if you have a lower amount of entropy to start with, then the change in entropy is, on a percentage basis, more impactful. So what we're saying is that the change in entropy of the surroundings is proportional to the heat transfer. And we're going to use Q rather than delta H, although under some circumstances Q and delta H are equal. But the Q says that you can monitor the change in heat transfer from system to surroundings without regard to pressure or volume. If you introduce pressure or volume, then you're stuck with delta H. So it's directly proportional to Q and inversely proportional to temperature. So as a matter of fact, if you choose your units of measure correctly, you can replace this with an equal sign. So if we choose this as joules and temperature as Kelvin, then we can say the change in entropy of the surroundings is equal to the change in energy delivered to the surroundings in terms of heat and inversely proportional to the temperature. So this just says as the temperature increases, the effect of heat is less, right? They work opposite one another. So if you decrease this one, you increase the effect of a change in heat, and that gives you a larger delta S. But if you increase this one, then the same change in heat energy provides a smaller value of change in entropy. Okay? All right. Let's see. So what would that mean for an exothermic process? An exothermic temperature in Kelvin is always a positive value, right? That's why we use Kelvin, because it goes from 0 to something, and it never goes negative. So this term is always positive. So we really only have to concern ourselves with the sign of that one. So if the sign here, if this is endothermic, then that makes this one negative. And if it's if it's exothermic, no. All right. Let's go back to exothermic. If it's exothermic here, then that would mean this is going to be, that would be negative. Oh, I know what it is. In order to maintain sign conventions, we need a negative sign in front of this. So that means if this is exothermic, it's negative, times a negative is a positive. So that gives us a positive delta S for surroundings. If this is endothermic, then it's positive, and that gives us a negative sign here. That slide's not a good explanation. All right. So there's our formula. We can use enthalpy if the pressure is constant. So in my let's see. Now I think the explanation is coming. If pressure is constant, then Q equals enthalpy. And that also means that delta S for the surroundings is equal to a negative delta H divided by temperature. So as long as pressure is constant, we can interchange delta H and Q. And chemists will often conduct their experiments at constant pressure so that they can interchange these two, because you can measure that one, but this one is derived. Or this one is more difficult to determine if you let the pressure change. Sometimes you have to do it. But for simplicity's sake, keeping the pressure constant allows you to measure enthalpy and use enthalpy in this calculation. Let's see. I'm looking at, I must have, Well, it's not doing what I expected now. It's missing. Oh well. Unless I'm not going back far enough. No, okay, that's fine. I must have explained the this relationship back in thermochemistry in chapter 6. You can prove it mathematically, that if the pressure is constant, then the delta H and Q are equal. So, at this point, you just have to take my word for it. Or go back to chapter 6. It might be in the textbook. I haven't looked to see. All right. So, the relationship, let's put this back up here. The delta S total is equal to the sum of the delta S for the system plus the delta S for surroundings. So any change, if this does not change, then if you change that one, this one increases, that one decreases, vice versa. Using delta S, in this case, the authors are referencing delta S universe. I'm saying it's total. So if delta S for total is positive, then the process is spontaneous, without question. So that means that if a change in, now, if we let that change, right, if that's going to be positive, then if these two are positive, change, if they both change, increase, then that has to increase. And that means spontaneous. If both of them are negative, then that's negative and that's non-spontaneous. Okay? Those are definite. If one is positive and the other is negative, then it depends on the conditions. Right? So if this one's positive and that one's negative, it's only spontaneous if the change in entropy of the system is larger than the change in entropy for the surroundings. Right? If this dominates, then it's spontaneous. And the other way around, if this one dominates, then that one's spontaneous. Otherwise, they're non-spontaneous for the opposite. If this is larger or that's larger, then you get a non-spontaneous. So that is conditional. These two situations are conditional. All right. So all of this is true, but it's difficult to work with when you're trying to describe a system and mathematically, if you calculate various values that are associated with the system, then this is very difficult to deal with. So, and Josiah Willard Gibbs recognized that fact, and he also wanted to know when these changes take place, we can calculate the amount of energy, the delta H, the enthalpy, that's available from a system. But what he wants to know is how much of that energy is actually available to do useful work. So he invented another term, delta G, for free energy. Now, there are other researchers, other chemists, other physicists, who have applied different types of free energy. That's too broad a subject for us to dig into the other possibilities. This is the most common and the most widely used term for free energy. And when we say free energy, that is the amount of energy that's available to do useful work. And what Gibbs discovered was that that energy is derived from the enthalpy, but minus a sacrificial amount that goes to entropy. So this free energy is based upon enthalpy, but we have to remove the amount that is not available for doing useful work, and that's the entropy term. Right? Now, why do we have to stick a T out here? Because the units of measure here are joules K. And these are all joules. Right? So you have to have a term here to cancel temperature. Otherwise, you can't add apples and oranges. These are apples. That's the orange. Multiply by temperature to turn it into an apple. Okay, so that's the Gibbs free energy equation. Delta G equals delta H minus T delta S. Now, we can say something about spontaneity in terms of the free energy. Okay, we're going to get to it, but I think, let me say a few words about this now. Just like that, and like that. Let's talk about signs. If delta S is positive, well, let's do it this way. If this is an exothermic reaction, and delta S is positive, we determined earlier that that would be a spontaneous reaction. Right? We had an exothermic and a positive delta S for our system. Then we would have a spontaneous situation. What would the sign of delta G be in that case? Well, if this is positive times negative, this is negative, negative, that would be negative. So what that says is, if delta G is negative, you have a spontaneous process. How would we get negative out of some other terms? Well, if we have positive here and negative there, that makes both of them positive. This is endothermic plus entropy is decreasing. So that would be a positive value here, and that's non-spontaneous. This is spontaneous. Okay? Now, what if both of them are positive, endothermic and increasing entropy? Well, in that case, that would be positive, this would be negative, and it wouldn't be spontaneous unless this term were larger than that term. So there's another conditional. It's only spontaneous if T delta S is greater than delta H. And the other way, negative, negative, it's only spontaneous if delta H is greater than T delta S. Okay, so these are definitely spontaneous, non-spontaneous. These are conditional. I think I've got another slide on it, but stream of consciousness, I thought this was the best place to put it. for today. All right. So here we have the authors giving us delta S universe, which is delta S total, actually. And delta S total is equal to a negative delta G over T. That's for constant temperature and pressure. So, take this one on faith. I don't know, we might be able to derive it. I just don't have enough time to do it right now. You should be able to derive this one from that one. But in that case, you have to say something about this in order to create that. Okay. So if the free energy decreases here, if that's negative, then that makes this term positive. That's positive, and we have a spontaneous reaction. Also, we still have, just to review, the delta S for the surroundings is equal to minus delta H over T. So we could say this is equal to that one plus system. And then we run out of time. So I'm going to have to go to the next slide. So let's look at these terms in turn relative to a liquid that is vaporized at its boiling point. Remember, at the boiling point, you have an equilibrium situation. All right. So what would be the signs of each one of these? At the boiling point, well, in this case, we would have to define system and surroundings. But is there work being done? Is there work being done on the system, or is there work being done on the surroundings? Well, in this case, we're saying that the system is the liquid. The system is the liquid. And if we allow it to expand, it's doing work on the surroundings, which makes it negative. So what's happening to heat? How do we get that liquid to boil? Well, we have to add heat to it, don't we? So Q should be positive. All right. Heat is required for that to happen. Delta H is proportional to Q. Right? If we maintain pressure constant, then these two are equal to one another. How about delta S? And here, delta S, if delta S does not have a subscript, then you can assume it's delta S total. Right, so delta S total, or the authors would call it universe, the delta S total is that as you add energy, you're increasing the entropy of both of them as it boils. gas is more disordered than liquid. How about the surroundings, though? What's happening to delta S of the surroundings? Here we're saying that this is converting to gas in the system, and the surroundings, in order to make that happen, have to transfer heat into the system. So, in effect, what we're doing is we're decreasing the energy entropy of the surroundings. They're decreasing. Okay, that's where that term comes from. How about delta G, free energy? At the boiling point or the melting point, delta G is 0. There's no energy available to do useful work. That's what that's saying. So if delta G is 0, you're at equilibrium. All right. In that case, if we say that delta G is 0, if this is 0, then delta H is equal to T delta S. Right? And that's at equilibrium. That's a useful relationship, because if you know that you're at equilibrium, boiling point, melting point, then you can say this: delta H equals T delta S. Yeah. Let's see. I'm going to do it on time. Time's okay. So let's try this problem. The value of enthalpy of vaporization of a substance, whatever it is, X, that's the substance, is 45.7 kilojoules per mole. And its boiling point is 72.5 degrees. So we're given delta H of vaporization is equal to 45.7 kilojoules per mole. And the boiling point, which is at this temperature, is 72.5 degrees centigrade. We're going to need Kelvin anyway, so let's just go ahead and add 273. So that would be 345K. Okay, let's calculate the total delta S, the delta S surroundings, and the delta G vaporization for 1 mole at the atmosphere. Okay. So under these conditions, what did we say about boiling point? Delta G is always 0 at the boiling point. Okay, that's the easy part. Delta G is 0. All right. Delta S is this relationship, surroundings equals negative delta H over T. All right. So if we, and delta S, this is just a side note, which is important. delta S's are reported in the literature in terms of joules per mole, per k-mole. So whenever you have kilojoules, if you're going to calculate delta S, you might as well change it to joules. So this would be times 10 to the third joules per mole. Right, so now we can calculate this one. So it's negative 45.7 times 10 to the third joules per mole, and temperature of 345.5 K. So that's joules per K mole. That's why the units are like that. And that turns out to be minus 132 joules per K mole. Okay? And then at equilibrium, the total delta S is also equal to 0. So the change in at equilibrium, that's 0. All right, that's important, at equilibrium, which is boiling point or melting point. In this case, boiling point. So if we can say delta G is 0, delta S total is 0 at equilibrium, then any value we calculate for delta S surroundings using that formula, we can say change the sign, that's delta S for the system as well. Right, just change the sign, you got this one. So really the only calculation we had to do was this one. Oh no, I forgot. We did have to do that one. So this one is going to be just the positive 132.
Spontaneous reactions occur as soon as two chemicals are combined. Like a ball rolling from the top of a hill, the reactants start at a high potential energy, and the products are at a lower potential energy. Potassium in water is an example of such a reaction. The reaction begins as soon as the two materials are combined. The reaction products are aqueous potassium hydroxide and flammable hydrogen gas.
Okay. I can't argue with that. In fact, you can add any of the alkali metals, lithium, sodium, potassium, rubidium, cesium, add them to water, and you get a similar reaction. You get the alkali metal hydroxide in solution plus hydrogen gas. The only difference is, as you move down, the enthalpy of the reaction becomes more and more exothermic. So you add sodium to water, you get a lot of heat, but it's usually not enough to ignite the gas as it meets with the atmosphere. But you add potassium, and there is sufficient heat to exceed the activation energy of hydrogen with oxygen, and you get the flames. Anything below potassium will also be a violent exothermic reaction and a secondary reaction where the hydrogen combusts. Okay, so this is the slide that I was referencing earlier, and this came straight out of the book. So what happens if S is positive and H is negative? Doesn't matter what the temperature is, it's always spontaneous. If S is negative and H is positive, so that's positive and negative, which makes that a positive, delta G is positive, and that one is always not spontaneous at any temperature. But the reverse process is spontaneous at any temperature. So then the question is, what happens when both are positive? Well, you only get a spontaneous reaction if S is positive and H is positive or endothermic. That only happens at high temperature, because that introduces this term very high that makes the total term negative and exceeds the positive term here to make delta G negative. So high temperatures favor endothermic with high entropy. For the other possibility, if both are negative, negative and negative, then you get a spontaneous reaction only if you can decrease this term below that one in absolute amounts. In other words, with a small t, then this term becomes insignificant, and now you have a spontaneous. So if both terms are negative, then you need low temperature. All right. Let me see. Okay, I think we have enough time. So if we have a gas that's A2, it's diatomic, and reacts with a gas B2, diatomic, to form gas AB at constant temperature and pressure, the bond energy of AB is much greater than that of either reactant. So let's put that on the board. A2 plus B2, and these are all gases. A, B gas. Now that means we need two of those to balance it. All right? And we're saying the bond energy of AB is greater than that of either of these. So we're saying here and here, here. So the bond energy here is greater than either one of those. So what does that mean? If the bond energy is greater, that means you have to add energy to that to break that bond and get it to go back this direction. That means the reaction is exothermic. You got, which means this is at a lower energy state than this side. So that means delta H is negative. It's exothermic. All right. So the signs here, we just did delta H. Hold on that for a few minutes. So if this is what I just said, if the energy of the reactants is greater than the energy of the products, you have an exothermic. And this means E means bond energy. And it's best to look at that one in terms of the reverse. If the bond energy is stronger here than either of these, you've got to add energy here to get it back to that place. So if you add energy in this side, you had to get energy out the other side. Recall when we're talking about Le Chatelier's principle. Put the energy term over here, because if these energies are higher, then when you form that one, that energy's got to go someplace, and it becomes a product. Right? So this is an exothermic reaction, and that means delta H is negative. Yeah, there's delta H is negative. So if we know that delta H is negative, and the temperature is constant, then delta H is negative times a negative makes positive surroundings. Right? So there's your positive surroundings derived from that expression, simply because we know that delta H is negative. So that makes this term positive. How about the delta S of, what did I say, system? No, I misspoke earlier. If delta S has no term, that is equal to system. Right. Delta S of system in these slides and in your author's book, delta S system. I should go back in there and put that delta S system in there, because that can be confusing. So what would the delta S for the system be? We don't know for sure. There's no way to tell. It's possibly about 0, but we don't know for sure. But in order to make any prediction of delta S universe, we have to know what the delta S system is. Right? And if we don't say it's 0, then we can't say anything about delta S universe. If we say that the system entropy is 0, then we can say that the universe is positive. Or the total, universe total, is positive. Right? That's the one kicker right there. What is that value? We don't know for sure. All right. So we talked about first law of thermodynamics, or conservation of energy. Second law of thermodynamics, delta S for the universe is always increasing. And another way that's expressed for the second law very often is they just quote Gibbs' equation. Along with delta S for the universe is always greater than 0. But there's the third law. It's not as important for us. It's just for information purposes. And it just says that the absolute entropy of a perfect crystal at 0 K is 0. In other words, there are no microstates available for a perfect crystal at 0 K. Which is another way of saying that from that point on, entropy is always increasing with temperature. Okay, so what if we are presented with a problem that requires a calculation, and we have a table of values? Can you calculate the delta S for a reaction? Well, the answer is yes. And the reason we have this little 0 here is these are standard conditions. Right? Under standard conditions, 1 atmosphere, 0, not 0 K. Standard conditions are 25 degrees. Standard temperature and pressure. And 1 molar for any solutions. So you can calculate it just like we did with enthalpy, right? Enthalpy, change in enthalpy for a reaction is the sum of the changes in enthalpy for the products minus the reactants. That's what that means. This is analogous to the enthalpy calculation. But the difference is, for enthalpy, the enthalpy is 0 for elements
in their standard states.
But for entropy, since entropy is measured in terms of 0 at 0K in a perfect crystal, there's always an entropy value. Right, so when you see a list for whatever the substance is here, and then you have delta H's, standard delta H's for that substance. If it's an element, this will be 0, but this will have some value. All right. So here we have a possibility. For this reaction, sodium plus water yields sodium hydroxide and hydrogen. Calculate the delta S. So here are the delta S values. And you just say 2 times sodium hydroxide, which is 50, which is 100. And then 1 times hydrogen, which is 131. So that's 231 for the products. Then minus the reactants. So 2 times 51 is 102. And 2 times water is 140. So that's 140 and 102 is 242. Right? So that should be 11. A negative 11 joules per K mole. Okay? Oh, there it is. We left out the mole here. It's understood when you calculate delta S, it's in terms of 1 mole. No, I take that back. What have we done in this calculation? We've multiplied the number of moles here times the value. Right? So the moles cancel out. So that is true. That's not per mole. That's for their reaction. We canceled the moles by the calculation. All right, how about Gibbs free energy? Same thing. If you know these values, you can calculate Gibbs free energy. Or if you know the reaction and you have a table, you can do the calculations just like we do for enthalpy, just like we do for entropy. Now, why is that possible? Why can we do that? Here's why. Because delta S, delta H, delta G are all state functions. It doesn't matter how you get there in a chemical reaction. Once you've got the overall reaction, all that matters is reactants and products. So that's why these calculations work, because it doesn't matter the path. It only matters beginning and end. All right. So, what do we got here? A stable diatomic molecule spontaneously forms from its atoms. All right, so what's the diatomic molecule? All right, let's say X. There you go. And it spontaneously forms from its atoms. So that means 2X over here. All right, what can we say about the signs? Well, I think it's best to look at delta G first. The key is spontaneous. If it's spontaneous, delta G has to be negative, less than 0. Okay? The enthalpy of these reactions you have no bonds here between the two. You got a bond there. So delta H should be exothermic. You give up energy when you go from here to here. And you have to put in energy here to go back to there. So if we know these two, what can we say about delta S? Well, we don't know the temperature, so we can't use the Gibbs free energy calculation. But we can rationalize it by saying you're going from 2 here to 1 mole there. So delta S is decreasing. Right. So let's see if I got those right. Negative, negative, negative. They're all negative. Okay, and there's your rationality. All right. Hold on a second. Let me check something. Just want to be sure I don't run out of time. I've got time to do this problem. So here we got a system of phosphorus trichloride plus chlorine gas yields phosphorus pentachloride. And the delta G is this much free energy, kilojoules, for that reaction. What happens to the ratio of the partial pressures of PCl5, the ratio of partial pressure on this side to the partial pressure on this side if the temperature is raised? We know from this equation that this is negative, so it's spontaneous. But do we need that to talk about the partial pressures? That's the question. So what would the ratio look like? The ratio of the partial pressure of PCl5 to PCl3, partial pressure, PCl3, pressure there, 5. Okay. You really can't tell from looking at that reaction that the partial pressure would change. Except that what? You can say something about the total pressure because you're going from 2 moles here to 1 mole there. So the total pressure should decrease. But the pressure of this versus that, how is that affected? Oops, I went too far. Okay, so let's the delta S for this is unfavorable because you're going from 2 to 1. But we know the reaction is spontaneous because delta G is negative. So that's where this equation comes in. Delta G equals delta H minus T delta S. If this value is actually negative, we're saying, because it's unfavorable, and this one is negative, which means it's spontaneous, then what can we say about this one? Well, if that's negative, and this term is positive, how do we get that to be negative? The only way to make this one negative after this one is positive is that one's negative. It's exothermic. So delta H would have to be negative. That means the temperature is increasing in our reaction. So as the temperature is increased, as we increase the temperature, if we increase the temperature, then we make this one more and more positive, which you eventually reach a point where delta G is positive. I'm not explaining that very well. Perhaps we ought to let that dog lie for the time being, so that we don't run out of time. We need to introduce one other topic. And what is the effect of pressure or concentration, depending on the reaction, on the actual free energy term, if we know what the standard free energy term is? We know what that one is, then we need to see if we're at equilibrium, then that's going to be zero. I mean, this is going to be zero. If we're at equilibrium, that will be zero. But this is under standard conditions. So if you have a reaction which is all gases, you can use pressure. If you have where you have concentrations, then you need the Q value. Because if you use a K value, you know that delta G is equal to zero. Right. We've already looked at this with the video that we just saw. So let's skip that. Let's move on to this one. Equilibrium occurs at the lowest value of free energy. The lowest value of free energy is zero. So if we're at equilibrium and this is equal to zero, well, before that, we had this. Right? But if we're at equilibrium, now this is equal to zero. And equilibrium is always K, equilibrium constant. Now we have a way to either calculate delta G from K or K from delta G. So now delta G 0, delta G is 0 at equilibrium, so we can calculate delta G 0 under standard conditions if we know K. Okay. We don't have time to deal with this one right now. It doesn't add much to the conversation. Let's look at these in terms of what does this equation mean now? Right. We just got through studying K's, and now we're going to relate them to the free energy, the standard free energy of a reaction. So, if the standard free energy is 0, then K has to be 1, right? Because the natural log of 1 is 0. So 0 times these terms would be 0. So if delta G is 0, then K is equal to 1. That's a good starting place. If delta G is negative, then this value has to be positive to give us a negative term here. Right? And the only way that K can give us a positive value is if it's if this is negative. K has to be positive. and vice versa. If this is positive, K has to be negative. Okay. So those are some generalizations we can make about the relationship of delta G under standard conditions, and K. Now, remember what Gibbs was trying to accomplish. When he created the formula, Gibbs was saying that delta G represents the amount of energy that's available to do work, right? Which means that delta G is equal to the maximum amount of work that can be derived from a process. That doesn't mean that you're going to get all of it out, because what have we left out of this? Well, energy losses such as friction, right? So this is the maximum amount of work. Delta G will supply a maximum amount of work under certain conditions. So that just means that it's hypothetical. Any real pathway, and that's a good point here, because this is a state function, this is a path function. Right? So they're only equal if the path allows for all of that energy to be converted. This depends on what path you take. This does not. The only time that these are exactly equal is for reversible. Processes. If the process is reversible, then you can extract the maximum amount of energy. All right? That never occurs because all real processes are irreversible. There's some loss in the process, which means that it effectively goes one direction. If it goes in the reverse direction, you'll lose more. So backwards or forwards, it doesn't matter. Irreversible means that you lose something in the process. All right, these are some handy, actually funny definitions. Well, the first law of thermodynamics says you can't win. You can only break even. In other words, you can't get more energy out of the system than you put in. Conservation of energy, right? Problem is, the second law says you can't even break even, because any transfer of energy will result in some waste of the energy, and the waste in terms of an increase in entropy. Because if this is the maximum amount that you can get from a process, you're always going to lose some of it. So the second law says you can't even break even. So what does the third law says? There's no way out, because you can never get to absolute zero. If we had absolute zero as a coupling point with any reaction, we could extract the maximum amount from it in terms of transfer of energy. All right. Oh, that's it. I'm done. So this is Thursday. Next Tuesday, we'll look at the review document. And hopefully, after you've had a chance to look at some problems and struggle with solving those problems, that we'll be able to coalesce some more coherent understanding of spontaneous reactions, entropy, and free energy. Okay, any questions before we call it a day?